Okay, so this will be the second lecture out of chapter 6. So in this lecture, one thing we'll talk about is calorimetry. So how do you measure heat changes in a process or a chemical reaction? So one method to do that is to use an instrument known as a calorimeter. So a calorimeter looks something like this. So basically you have a container, a big container, and then inside that big container you have a smaller container, which is where the system is at. And then the larger container is filled with water, and then you have a thermometer in there, and you have a stirrer in there. So thermometer to measure the temperature change of the water, and a stirrer to make sure there's no localized pockets of water that are at different temperatures, right? You want to keep all of the heat change dispersed throughout the entire calorimeter. So in this case, so if we took an example reaction, so maybe if we took 1 mole of methane, for example, and 2 moles of oxygen gas and put them into the smaller cube, so that's the system, that's the reaction under study. So then if you ignite that, then they react to make a mole of CO2 and 2 moles of water. And then does that reaction give off heat, or does it absorb heat? Or it could be thermoneutral. There are some reactions that don't give off or absorb heat or energy, but most of them do give off some heat or absorb some heat. Okay, so the system goes in the small cube, and then everything else is the surroundings. So the water is the surroundings, the stir, because when the temperature change of the water, if the water changes temperature, the stir is going to change temperature too, right? The thermometer is part of the surroundings. The containers themselves are going to change temperatures, right? So they're part of the surroundings. So everything else is the surroundings, and only the chemical reaction itself would be the system. Okay, so if the temperature of so you did this reaction, methane combusted with oxygen to make CO2 and water. If the temperature of the water went up, was the system an exothermic reaction or an endothermic reaction? Well, if the temperature of the water went up, then the CH4 plus O2 must be giving off energy, right? And where does that energy go? Where it heats up the small container, and then that in turn heats up the water, which in turn heats up the thermometer, right? So if the temperature of the water went up, then that would be an exothermic reaction with respect to the system. With respect to the surroundings, it would be endothermic because the surroundings is absorbing energy. So what if the temperature of the water went down? Well, that means if the thermometer is cooling off, then the water is cooling off. If the water is cooling off, then that means it's losing some energy to whatever reaction would be occurring inside the smaller container. So that would mean the reaction itself would have been an endothermic reaction. So if the temperature of the water goes down, then that means the reaction, the system would have been endothermic. So with respect to the reaction, it would be endothermic. With respect to the surroundings, it would be exothermic because the water and the thermometer would be giving off energy and they would be cooling down, right? So again, in thermochemistry, you always have to know what you're talking about, the system or the surroundings, because one of them is exothermic and one of them is endothermic unless it's a thermoneutral process. Okay, so using a calorimeter, you can determine Q or delta H. Using this equation, right? Q is equal to C times delta T. Or if it's a chemical, so that would be if it's a process, or if it's a chemical reaction, delta H, right? Enthalpy is C delta T. So C is a constant. It's called the heat capacity of the calorimeter, right? So it's going to take a certain amount of heat to cool or heat the containers and the water and the stir and the thermometer, right? So every calorimeter has its own heat capacity. And then delta T is a change in temperature. So it's T final minus the initial temperature. Okay, so if you want to figure out what C is, one way to do that is you must use a process or a reaction where delta H or Q is already known. So if this chemical reaction, CH4 plus O2 to make CO2 and water, if delta H was known for that reaction, then you could do that reaction in the small container and you can measure the temperature difference. So if you know Q, and if you can experimentally you can measure T, then you can calculate C, right? C would just be equal to Q over delta T, or delta H over delta T if you knew what Q or delta H was. So if you studied a known reaction in the calorimeter, you can figure out what C is, and then once you know what C is, then you can use that to study reactions where you don't know what Q or delta H is. Okay, so some similar equations that you should know and know how to use. So Q, heat of a reaction or process, is equal to M. So M is the mass of the substance in grams, times C sub S. C sub S is what's known as the specific heat capacity of the substance. So that's simply the amount of heat needed to raise the temperature of 1 gram of the substance by 1 degree Celsius. And that's a constant. And then delta T. Or similar equation, Q is equal to N C sub P delta T. So the only difference between the two equations is one is dealing with grams and one is dealing with moles of the substance. So here in this case, N is the moles of the substance under study, and C sub P is the molar heat capacity. So it's the amount of heat needed to raise the temperature of 1 mole of the substance by 1 degree Celsius. So the specific heat capacity and molar heat capacity, so those are values that are known for a lot of different substances, and those values can be found in thermodynamic tables. So either within your chapter or in the back of the textbook, or you can Google search the internet and find large numbers of thermodynamic values for lots of different substances. So we just take a few to illustrate the concept. So aluminum, copper, iron, ethanol, and water. So this C sub S, so that's the specific heat capacity, right? So you need 0.901 joules of energy to raise the temperature of 1 gram of aluminum by 1 degree Celsius. Or you need 0.384 joules of energy to raise the temperature of 1 gram of copper by 1 degree Celsius. So which would be a better conductor of heat? So which one? So on a gram to gram basis, it doesn't require as much energy to change the temperature of copper as it does aluminum, so copper would be a better conductor of heat, right, on a gram to gram basis. Or the molar heat capacity is just moles of substance, right? Okay, so let's take some example calculations. So how much heat is required to raise the temperature of a 12-inch cast iron skillet that has a mass of 1,265 grams. So if you want to raise the temperature from 25 degrees Celsius to 80 degrees Celsius. Okay, so which of these equations do you use? Well, you were given grams of substance. So you're going to want to use this equation, right? Because this equation, the specific heat capacity is dealing with grams. The unit has units of grams. So we simply take the mass. So we need that equation. So we simply take the mass of the iron, and we take the specific heat capacity of iron and the change in temperature. So T final minus T initial. So if you multiply that out, then you get 239.2 joules, or divide by 1,000 to convert to kilojoules, so 31.239 kilojoules. Okay, so a similar problem. So how much heat? So let's say you have the cast iron skillet. But now it's full, it's got 3 cups of water in it. So how much heat is needed to raise the temperature of the 12-inch cast iron skillet that has a mass of 1,265 grams from 25 to 80 degrees Celsius if the skillet has 3 cups of water in it, right? Assuming that there's no evaporation of water in the process. Well, now if you want to calculate the heat, you have to calculate the heat of both the skillet and the water, right? How much heat is needed to change the temperature of both. Okay, so for the water, the first thing that we need to do is we have 3 cups. We need to do some conversions to figure out how many grams that is. So we need some conversion factors, right? So there's 1 gallon is the same thing as 16 cups. So then cups will cancel. And then 3.7854 liters in 1 gallon. So now gallons will cancel. And then convert liters to milliliters. So 1,000 milliliters per liter. So then liters would cancel. And then we would need the density of the water to convert from milliliters to grams. So water's density is approximately 1 gram per mil. So then mils cancel. So that 3 cups would be 709.8 grams. And so now we can use this equation, right? MC delta T. So plug in our mass, so M. Plug in, so this would be C sub S, the specific heat capacity for water, right? You just got to go to the table and you got to look it up. 4.18 and know the units, joules per gram degree Celsius. And then the temperature, T final minus T initial. So let's see what's going to cancel. So grams are going to cancel, degrees Celsius are going to cancel, and you have joules that are left, right? So 163,174 joules, or 163.174 kilojoules. So now we can calculate the total heat. So take the heat from water, so the heat needed to raise the temperature of water, plus the heat needed to raise the temperature of the iron, and add the two together, it would require 194.3 kilojoules of energy to raise the temperature of both of them from 25 to 80. So if you notice, it takes a lot more energy to raise the temperature of water than it does iron, even though you have 709 grams of iron, of water, but you have almost twice as much grams of iron. But it takes a whole lot more energy to raise the temperature of water than the iron because water has a much higher specific heat capacity. Okay, so similar to this, so this heat's a phase transition. So this is a heating curve for water. So if we start at negative 20 degrees Celsius, of course you would have ice. And if you start adding heat to ice at a constant rate, well, the ice is just going to warm up until it hits 0 degrees Celsius. And then what's going to happen at 0 degrees Celsius? It's going to start to melt, right? So if you're going this way, it's going to melt, or if we were going the opposite way, it would freeze. So at this temperature at 0 degrees Celsius, okay, so let's do this. So here we're just warming the ice, no, not that. Here we're just warming the ice up. And then we hit 0 degrees Celsius. Well, so it's 1 second. So ice has its own specific heat capacity. So you need 2.05 joules for every gram of ice to raise its temperature by 1 degree Celsius, or 38.1 joules per mole of ice. Okay, and then you hit 0 degrees Celsius, and so now here we're just warm. Now what's happening is the ice is melting to water, so the temperature doesn't change until all of the ice is melted. So at the right of this point would be where all of the ice is melted, and now it is just liquid water, but it's at 0 degrees Celsius. And so that has its own heat, so that process does. So that's what's known as the heat of fusion. So that would be from melting something. So you need 6.01 kilojoules of energy to melt 1 mole of ice at 0 degrees Celsius to make 1 mole of water at 0 degrees Celsius. Or if you're going the opposite direction, freezing it, then it would be negative, right? Liquid water would be giving off energy to make ice. Okay, and then the next stage, so here, you're just warming up the water, right? From 0 degrees Celsius to 100 degrees Celsius. And so you need 4.184 joules of energy to change 1 gram of water by 1 degree Celsius. So it takes more energy to warm up water than it does to warm up ice. And then at 100 degrees Celsius, what starts to happen? So that's the boiling point of water, right? So now at this stage, now the water is turning into steam. So you're evaporating the water, and that has its own heat associated with this. So you need 40.7 kilojoules of energy to evaporate 1 mole of water from liquid water to steam. So if you notice, it takes a whole lot more energy to convert water to steam to gas than it does to take ice to liquid, right? So why so much more energy? Well, when ice goes to liquid, so in ice, water is hydrogen bonded, right? And in liquid, water molecules are still hydrogen bonded to each other. But when you go from the liquid to the gas, then you have to break those hydrogen bonds, and individual water molecules escape into the gas phase by themselves. So you have to totally break the hydrogen bonds to take it to steam. So it requires a whole lot more energy for that process. And then lastly, on this heating curve, so in this portion, then now you're just warming up the steam, right? And so it has its own energy associated with that. So it takes about as much energy to warm steam as it does to warm ice. Okay, so let's use this for an example. So let's do some calculations with this. So how much heat is released when a Zamboni resurfaces the ice at an ice skating rink? So if you know what a Zamboni is, so if you've ever been to ice skating rink or if you've been to a hockey game, every now and then they make all of the skaters get off the ice, right? And then this Zamboni comes out and it resurfaces the ice, basically makes it smooth again. So how does it do that? So it puts down water, and then that water freezes, and then it scrapes the surface to make it smooth. So if the Zamboni uses 300 liters of water, starting at 40 degrees Celsius, and then the water cools off to ice, and the ice cools to negative 10 degrees Celsius. So how much heat would be released in that process? So to do this calculation, you would have to know what the density of water is. So the density of water at 40 degrees Celsius is 0.992 grams of water per mil of water. Okay, so this is a little bit involved calculation because you have to recognize the first thing you have to do. So we start here at 40 degrees Celsius. So the first thing you have to do is you have to cool the water. So that would be Q1, right? You have to cool the water from 40 degrees Celsius to 0 degrees Celsius. And then what you have to do is then you have to freeze the water. So from liquid water at 0 degrees Celsius to ice at 0 degrees Celsius. So that would be Q2. So you have to calculate that because liquid water has different specific heat capacity or molar heat capacity than freezing it does, right? And then once you have ice at 0 degrees Celsius, then you have to cool the ice off to negative 10 degrees Celsius. And so you have to calculate that heat as well. So that would be Q3. So you got to calculate Q1, Q2, and Q3 separately and then add them all together. Okay, so to do this, first of all, since we're starting with 300 liters, we need to convert that to how many moles is that? So 300 liters, we'll convert liters to milliliters, so liters cancel out. And then use the density to convert from milliliters to grams. So then milliliters cancel out. And then once we have grams, we can use the molar mass of water to convert. So grams cancel out. So inverse of the molar mass to convert to moles of water. So this would be 16,515 moles of water. So now we can use these equations. We can use that equation, right? Since we have the moles of water, and we know C sub P, we can look that up, and we know the temperature change. It's going from 40 to 0, right? So we take the moles of water times C sub P of water times the temperature change. T final is 0 minus T initial, so it started at 40. So that gives you negative 49,743,180 joules, or negative 49,743 kilojoules. So negative, so it's exothermic as it should be, right? Because you're cooling off the water, so it's releasing energy to the surroundings. And then we can calculate Q2. So Q2, so we're going to be using this. So it's already kilojoules per mole, and we just calculated the moles of water, so we can multiply the two together and let moles cancel out, and then we have kilojoules. So Q2 is a little bit simpler calculation, so we just calculated the moles times the heat of fusion, but it's negative since it's going from water at 0 degrees Celsius to ice at 0 degrees Celsius. So moles cancel, and then we have negative 99,255 kilojoules. And then to calculate Q3, then we need this, right? We need the specific heat capacity of ice. And so since we know the moles of water, then we want to use the 38.1 joules per mole degree Celsius. So we know the moles. We calculated that earlier, where you use the molar heat capacity of ice times the change in temperature. So T final, what's going to negative 10, it started at 0. And calculate that out, we get negative 6,276 kilojoules. So now we just add the three together, Q1 plus Q2 plus Q3, and we get negative 155,274 kilojoules of energy would be released in that process. Okay, let's take a similar calculation. So let's say we had a setup like this. So we have a container that's got liquid ammonia, and we want it to evaporate to gas. So if it's going to go to liquid to gas, it has to absorb energy, right? So where's it going to get that energy from? Well, we have it coupled to this chamber, which has liquid water in it at 0 degrees Celsius. And so if water gives up energy, so energy is going to flow this way, or heat's going to flow that way, right? So if water then cools off, it gives up energy to the liquid ammonia, so the water will freeze and the liquid ammonia will become gas. And then we have a compressor to compress the gas, so using the electricity back to the liquid. So then we can make ice in this process. Okay, so if you had 12.5 grams of ammonia, how many grams of water at 0 degrees Celsius could you freeze to ice by evaporating the 12.5 grams of ammonia? So how many grams of water at 0 degrees Celsius will freeze to ice at 0 degrees Celsius? Okay, so if we want to do that calculation, so first we need to convert the 12.5 grams of ammonia to moles. So we need the molar mass of ammonia, right? So this would be the inverse of the molar mass. So 12.5 grams times 1 mole per 17.03 grams, so that would be 0.740 moles of ammonia. And then we would need so it's going from liquid to gas, so it's evaporating. So we need the heat of evaporation. So we'd have to look that up, or it'd have to be given to you. So we calculated the moles, and this is kilojoules per mole. So if we just multiply the two together, moles will cancel. So then when that evaporated, to evaporate that, it would need 17.18 kilojoules of energy. Where is that energy going to come from? It's going to come from the water, which is going to freeze, so it's going to give up its energy to the ammonia. Okay, so now we can convert to moles of water by using the heat of fusion of water. So that would have to be given, or you'd have to look it up. So since we know the kilojoules, and then we would just take the inverse of the heat of fusion. So 1 mole is 6.08 kilojoules. So that means it would freeze 2.859 moles of water. And now we can convert to grams, right, using the molar mass. So if we have the molar mass of water, so the moles of water times the molar mass, so moles of water cancel, and that would give us 51.5 grams of water could be frozen by evaporating 12.5 grams of ammonia. Okay, so lastly in this lecture, I just wanted to try to correlate what we're studying in this chapter to what we've studied in other chapters. So I think it always makes learning chemistry a little bit more meaningful if you can see how things piece together. So this table just shows the heats of fusion. So that would be to melt something, right? Or the heat of vaporization to evaporate it from liquid to gas, so for some different compounds. So we can relate this to material that we covered in chapter 11, intermolecular forces. So the heat of vaporization, energy needed to evaporate 1 mole of a compound, and let's correlate that to boiling point. So if we take CH4, methane, ethane, propane would be the 3-carbon chain, and butane would be the 4-carbon chain. So as you can see, as the carbon chain increases, the heat of vaporization increases. So you need more energy to evaporate it. And of course, that correlates with the boiling point. Methane has a boiling point of negative 164. If you go to ethane, it's negative 88. To propane is negative 42. And then to butane, it's negative 0.5. So it takes more energy to evaporate butane, and so it has a higher boiling point. So why does it require more energy to evaporate butane, the 4-carbon chain, than methane, the 1-carbon chain? Well, we talked about this in chapter 11, right? If we looked at intermolecular forces. So the molecules are very nonpolar, so they don't have dipoles. But when they approach each other, right, their electrons will repel each other, and that will cause a distortion in the electron density. So that's depicted here, where we have kind of a bubble representing the electron density, and it's shifted to one side of the molecule because the electrons are repelling each other. So then one surface becomes partial positive and the other surface becomes partial negative, and so now there's a weak electrostatic attraction there, and that's called an induced dipole, or a van der Waals attraction, right? And then of course butane with 4 carbons, it's got more surface area, so there would be more attraction. So to make that molecule boil, you would have to break all of those intermolecular attractions. That's going to require more energy, so it's got a higher heat of vaporization, and consequently it has a higher boiling point, right? You have to go to higher temperature, more energy to make the molecule go from the liquid to the gas phase. Right, or if we take these molecules and compare them and throw in water and look at their heats of vaporization to go from liquid to gas. So they all have an OH, right? So if you remember, then OHs are polar. So if we look at the heats of vaporization, so they increase and boiling points increase as well, right? So they all have OHs, so they all have polar bonds. And if you remember, so hydrogen partial positive can make a hydrogen bond. Let's do different color. So that oxygen can make a hydrogen bond there, and this oxygen can make a hydrogen bond to that hydrogen, and this hydrogen can make a hydrogen bond there, and that can make a hydrogen bond there, right? So this one H2O molecule in the middle can make 4 hydrogen bonds. Right, so every water molecule can make 4 hydrogen bonds. And if we took the 2-carbon chain, so this would be ethanol, and this is methanol. Right, so this can make hydrogen bonds, but it can only make 2 hydrogen bonds, and methanol can only make 2 hydrogen bonds. So why does water have the higher boiling point and the higher heat of vaporization? Because you have to break those hydrogen bonds for one water molecule to escape into the gas phase, right? Whereas ethanol and methanol, you only have to break 2 hydrogen bonds for them to escape into the gas phase, so you don't need as much energy, so the boiling point is lower. So why does ethanol have a higher boiling point than methanol? They can both only make 2 hydrogen bonds, but ethanol has more surface area than methanol, so it would also have stronger van der Waals attractions, or London dispersion forces, or induced dipole attractions, right? So anyway, so basically, the concept that we cover in this chapter, heats of vaporization, relates very closely to these intermolecular forces that we talked about in chapter 11. Okay, and we will stop there.